For this lecture, we'll be having systems of ordinary differential equations where we will be dealing with real and distinct roots, complex roots, and the real and repeated roots. So similarly, what are the outcomes that we expect? Outcome A, knowledge of mathematics and physical sciences. Outcome J, ability to use techniques, skills, and modern engineering tools. And then for the learning outcome, it's the system of first-order linear differential equation with constant coefficients. So typically, how does it look like? Typically, you'll have something like this. So for example, derivative of x with respect to t is equal to a1x, b1y, c1z plus any function of t. And then similarly, the derivative of y with respect to t is this one, wherein a, b, and c are the constant coefficients of the variables x, y, and z. So in this case, if it's written in this form, the one on the upper left, we can translate it into a matrix. So how do we translate that into a matrix? So we say that the nomenclature that we have for the differential operators here, or the dx over dt, dy over dt, dz over dt, they can be written as the x prime. And then the constant coefficients, a1, b1, c1, they can be represented by capital A or the matrix A. And then x there is your x, y, and z. That is the variable matrix. Whereas your B in here, that corresponds to the functions of t. It can be a constant, it can be a function of t. So in the event wherein B, which is this one, is equal to 0, the differential or the systems of differential equations are considered or is considered to be homogeneous. Whereas if it's non-zero, it's non-homogeneous. So here, x prime, a, x, b. So let's just try for the first case because we have 3 cases. Actually, we have 4 cases, but then I'll just tackle 3. The fourth one, I'll leave it for you to try to read and understand because, you know, it's basically just a continuation of the first 3. So this one, let's go to the first case, which is the real and distinct eigenvalues. So if you have, for example, x prime is equal to ax, again, what's x prime? This is the derivative matrix, right? The differential operator matrix. A is, what do you call this? Coefficient matrix, and then x is the variable matrix. So if we have this, for example, what we do here is we assume a solution. So let x be equal to c e to the mt. So this is similar to what we had in our differential equations lessons, that this can be a solution. However, looking at this, the problem on top states that x prime is equal to ax. Since we let x be equal to c e to the mt, the first derivative of x is actually c e to the mt times the derivative of e to the mt, which is m. So let's plug in. So x prime is c e to the mt, x is c e to the mt, but then there's an a in front. So we have this. So if we transpose everything to one side, say a c e to the mt minus c e to the mt, we can actually factor out the c e to the mt, leaving us with a minus m, right, is equal to 0. Now, I have a question, guys. Why is it necessary for me to multiply everything by I? What is I again?
Identity matrix.
Why is it necessary for us to multiply everything by the identity matrix?
To transform into a vector.
Yes, because your A, you don't have a problem. Your A is already a vector. That's matrix. The problem is the M. M is the eigenvalue. It's not an eigenvector. It's a, you know, constant multiplier or just the constants, right? Scalar. So what we have to do here is multiply M by I so that this one becomes a vector. So since this line, 0 times I is 0, A times I is just A, M times I is MI. You can't just say M because M is non-matrix. This is a matrix. So if everything is equal to 0, that means either the left side is equal to 0 or the right side is equal to 0. But the problem is, guys, take note of this. E to the empty can never be 0. Why is it that e to the empty can never be 0? Because exponential, you take note that it can never be 0, right? It always has a value, a non-zero value. So that means where can it be 0? Some of you might say, sir, can C be 0? Yes, but the problem is if C is 0, there's nothing to solve. So A minus MI can be the only one that's 0. So here, what we do here is we try solving it. So A minus MI is what you call the auxiliary equation. A minus MI equals 0. And then C, take note there, C is a non-zero vector. It's also a vector. So what are the steps? These are important, guys. Please take note of these. Number one, after you do this, you can say that the A minus MI is equal to 0. And then we actually solve for M. M is the root of the auxiliary equation. And then number two, substitute M to this. This is what you call the characteristic equation. So ipa-plug in natin yung M to the actual given conditions. And then we try solving for the constants C1, C2, etc., the small letter C's. And after that, we look for the general solution. Of course, if we're given initial or boundary conditions, you could solve for the particular solution. But do take note in this case that solutions should be linearly independent. Otherwise, if they're linearly dependent, di ba? Either it's the same. For example, if you have two lines, linearly dependent siya, either intersecting siya at all points because it's the same line, so you have infinite number of solutions, or they don't intersect at all. Okay, so let's try. Let's just say this one. We transform everything first to an arranged method wherein x comes first, y, and then z. And then we transform it into a matrix form. So the matrix form here would be, this would be your x prime, this would be your a, this would be your x, right? And then here, I already gave you that when you solve A minus MI equals 0, you'll be able to get three roots. The three roots that you'll be able to get are 3, 4, and 5. So let's just go to this, but then I'll give you an example, an easier example. So you have a system of differential equations. As I said, the first thing that we need to do to solve this is transform it into a matrix. So I can see that x prime is actually equal to 2, 3, that's 1, and then 0. And then multiply that to x. X again is the variable matrix. So what is step 1 again that you saw earlier? The auxiliary equation, right? A minus mi should be equal to 0. So since this is the first step, let's try. What is A? Okay, A is 2, 3, 1, 0 minus M. I is the identity matrix. It should be equal to 0. So that becomes 2, 3, 1, 0 minus M0, 0, M. So when we combine them, that becomes 2 minus M, 3, 1, and then negative M. And then let's solve for this one. This is, let's solve for the determinant. As I said, this is a 2 by 2 matrix. It's easy for us to use the diagonal multiplication. Can you please dictate to me the determinant of this one. And then negative m, right? Minus 3. So negative 2m plus m squared minus 3 is equal to 0. M squared minus 2m minus 3 is equal to 0. Can you please factor this out?
Quantity m minus 3 and quantity m plus 1.
M plus 1, therefore, we can say that m is equal to either 3 or negative 1. What theorem supports this one? That when you have two terms that are being multiplied and then that's equal to 0, either the first term is equal to 0 or the second term is equal to 0. What do you call this theorem? Zero factor theorem. Zero factor theorem states that when you have a times b is equal to 0, either a is 0 or b is 0. So again, 3 and negative 1 are the eigenvalues. Okay, so let's take note. A here is 2, 3, 1, 0. The two values of m are 3 and negative 1. And then according to step number 2, it says there, what? M into the characteristic equation. So what is the characteristic equation again? So how do you do that? It's basically a minus mi multiplied to c1, c2, and so on is equal to 0. So for, we have two letter m's. M is equal to 3. Let's just say for the first one, what happens is a minus mi daw. So I can say 2 minus 3, 3, 1, negative 3, C1, C2 is equal to 0. So how did I know how to write this? Look at this. A minus mi. So it's A minus m times I. So mi becomes m00m. So it's basically like subtracting m from the first, subtracting m from the element 2, 2, subtracting m from the element 3, 3. So the main diagonal. And then multiplied to, how many variables do I have? 2 variables. So that means 2 constants. And then lastly, equal to 0 because characteristic equation is equal to 0. So how do we deal with this? So this one is negative 1, 3, 1, negative 3. C1, C2 is equal to 0. So using the first line, because isn't it that when you multiply matrices, it's always row by column? So I can say negative C1 plus 3C2 is equal to 0. So I can say this is equation number 1. But what you notice here is that using equation number 2, the row plus negative 3, C2 is equal to 0, equation 2, they're actually just the same. So I can't cancel out anything. So what do we do? What we do here is maybe from equation 1, negative C1 plus 3C2 is equal to 0. I can see that C1 is actually 3C2. Can you follow this, guys? So here, if we let C2 be equal to 1, what is the value of C1, guys? 3. Therefore, I have a solution. X1 is equal to C1, capital C, and then 3 e to the, what's the root? The root is 3. And then look at this, guys. You might say, sir, what's this C1 again? That's a capital C. This is a small c. I'll show you as we go on. So take note that we have two roots. For m is equal to -1. Let's plug that in. 2 minus -1, 3, 1, minus -1. C1, C2 equals 0. All right. So that means this one is actually 3, 3, 1, 1. C1, C2 is equal to 0. So when I multiply, I can say 3C1 plus 3C2 is equal to 0. This is your equation number 1. Equation number 2 is basically C1 plus C2 is equal to 0. So again, similar to the first one, they're just the same. So I can say that the easier one, of course, is equation 2. So I can say that C1 is basically negative of C2. So what can we assume? If we let C2 be equal to 1, what is your C1, guys? -1. Therefore, I can say that my second part of solution is that it's C2 -1, 1 e to the negative t. Therefore, I'm already finished solving this because look, there are only two eigenvalues. I was able to substitute this because according to the steps, first step here, what do you call this, guys? Auxiliary equation, solve for the eigenvalue. Number 2, plug in the eigenvalue in the characteristic equation to solve for the constants. And then now that you have the constant solved, you have the general solution. So in our case, we have two eigenvalues in here, 3 and -1. That means you have two separate solutions. And then what we do here is the general solution is, of course, x1. So that's C1, 3, 1 e to the 3t plus C2, -1, 1 e to the negative t. All right. Some of you might ask, sir, we only assume this. Is it possible to assume that C2 is equal to 2? It's okay. This one would be 6. So that the factor is kept the same. But some of you might ask, is it okay, sir, to assume that C1 or C2 is equal to 0? No. Because if C1 or C2 is equal to 0, the whole column becomes 0. If the whole column becomes 0, the determinant becomes 0. What happens if you have a 0 determinant? Here, the Wronskian determinant becomes 0. And if it's 0, it becomes linearly dependent. You had this way back in your differential equation. So that means the Wronskian determinant can never be 0 for it to be linearly independent. Okay, so let's go back. So x is, as I said, 3, 1 e to the 3t plus C2 -1, 1 e to the negative t. This was our solution earlier. And again, some of you might ask, sir, when I was solving m equals -1, I assumed that C2 is 1. Is it okay if I assume that C2 is the one that's -1? It's okay. If C2 is -1, your C1 would be the +1. The ratio is still the same. Okay, so if this is the solution, what are the other forms that it can appear? If I ask you to separate this, you can say, okay, sir, x is equal to 3 C1 e to the 3t minus C2 e to the negative t. Y is equal to C1 e to the 3t plus C2 e to the negative t. This could be an answer. Now, if I ask you, check for linear dependence. The Wronskian, where do I get that? There, from the constants, 3, 1, negative 1, 1. Okay, what is the Wronskian determinant? Minus negative 1, so the answer is 4. Since the Wronskian is non-zero, that means linearly independent. Okay. In this example, 3, 4, 5, 6, I'll give you another one example, and then let's try. So another example is this. So if I give you this, I'll provide you with the m's already, so you don't need to solve using the first step. 3, negative 2, 1. For this one, for m is equal to 3, let's try solving. What would be the given matrix? So that's 1 minus 3, that's negative 2, and then just copy this. So 1 minus 3, it's negative 2, and then negative 1, 1, and then this is negative 3. Did you get the same as me? All right. So this one, it's a 3 by 3 matrix. So that means you have 3 constants to solve. C1, C2, and C3, and then that's equal to 0. So what do you call this again? Yes, this one's the characteristic equation. Very good. Okay, now that you have this, what's the next step? This one would give us what? The possible equations. So you'll notice that, let's just say, let's use the first line, negative 2C1 plus 2C2 minus C3 is equal to 0. That is your equation number 1. The thing is, when you look at the second line, isn't it exactly the same, but it's the opposite signs?
Yes.
So let's not use that. Let's use the third one. So negative C1 plus C2 minus 3C3 is equal to 0. This is your equation number 2. Now it's up to you to cancel. What would you want to cancel out, guys? Can we cancel out anything? So let's just say multiply this by negative 2. So that becomes negative 2C1 plus 2C2 minus C3 equals 0. And then 2C1 minus 2C2 plus 6C3 equals 0, right? And then you'll see that you can cancel out C1 and C2. What will be left? You'll be left with 5C3 is equal to 0. So since 5C3 is equal to 0, I can say that my C3 is an actual 0. So we can say here that using C3 is equal to 0 and equation number 2, so I can say negative C1 plus C2 minus 3 times 0 is 0, so that cancels out. So I can say that C1 is actually equal to my C2, right? Now that we have a relationship between C1 and C2, it might be a bit safe to assume. What can I assume, guys? If C2 is equal to 1, that means the resulting C1 is also equal to 1. Am I correct? So your first x, because you have three eigenvalues, that means you will have 3 x's, 3 parts, right? So the first one would be what? C1 and then ABC, or 1, 2, 3, C1, C2, C3. What's C1?
1.
C2? What's C3? 0. E to the 3t. Because take note, that's also an answer. There. So C1, C2, and C3, you already have this. Okay? I hope it's quite clear. Let's go to the next. Take note that the matrix is 1, 2, negative 1, 2, 1, 1, negative 1, 1, 0. This is your matrix A. So for M is equal to the next one, which is negative 2. Can you please dictate to me the matrix? 3.
2, negative 1.
All right. What's this one?
2, 3, 2, 3, 1 po.
2, 3, 1.
Negative
And then you
1,
said
1.
negative 1, 1, 2. So that means you have 3 C's again. However, this one, all 3 are different. So it's better for us because 3 equations, 3 unknowns. C1 plus 2C2 minus C3 is equal to 0. Let's call this equation 1. I like it better if it's like this because we don't need to assume anything. Plus 3C2 plus C3 is equal to 0. Let's call this equation 2. And negative C1 plus C2 plus 2C3 is equal to 0. Let's call this equation 3. So I think the easier one to cancel out is probably 3, right? So let's just say eliminate C3. That's our goal. So using 1 and 2, let's just add them. So that becomes 5 C1 plus 5 C2 is equal to 0. Since I want to eliminate 3, let's just say 2 times equation 1 plus equation 3. So this is 6 minus 1. So 5C1. 2 times equation 1 plus equation 3. So plus 5C2. Oh, it resulted to the same, right? So 4 and 5 are the same. So what can we do? Okay, maybe we're left with an assumption again. We have to assume again. So from equation 4, let's just say 5C1 is actually negative 5C2, or C1 is negative C2. I can assume, right? What's your assumption? C2 is equal to 1. What is C1? Negative 1. So maybe let's solve. So i-plug in natin. So 3 times negative 1 plus 2 times 1 minus C3 is equal to 0. So this is negative 3 plus 2 minus C3 is equal to 0. What is C3, guys? Is it correct? Negative 1? So with this, I can say that I already have my C1, C2, C3. So my second solution is capital C2, C1, C2, C3, e to the negative 2t.
Yes,
So this
sir.
is the first, this is the second. Some of you might say, sir, what if I assumed C2 to be negative 1 so that my C1 is positive? It's okay. You'll be able to get C3 as positive 1 as well if you assumed the other way around. But then their ratios will be the same. So this one will be positive 1, negative 1, positive 1. And that's still correct. You know why? Kasi ganito. Isn't it that this C is any constant? Am I correct? So if I move out, guys, if I move out a negative sign in here, what would be the signs of this one? Positive, negative, positive. So yun na nga. And then how can you solve for the capital C1, capital C2, and capital C3? Only when I give you what? The boundary or the initial condition. So let's go to the third one. So based from this, your A 1 to negative 1, 2, 1, 1, negative 1, 1, 0. But this is for m equals negative 2. This is positive 3. Now we're solving for m is equal to 1. Can you please dictate to me the next matrix?
0,
Yes, 0.
2, negative 1,
Yep.
2, 0, 1, and negative 1, 1, negative 1.
So this one is C1, C2, C3 is equal to 0. So what about this one? Walang 0 siya. So that means 0 C1 plus 2 C2 minus C3 equals 0. Right? So next one is 2 C1 plus C3 is equal to 0. And then lastly, negative C1 plus C2 minus C3 is equal to 0. So I can say here that eliminate C3. So that means, let's say this is 1, this is 2, this is 3. So that means 1 plus 2 will eliminate C3. 2C1 plus 2C2 equals 0. And then eliminate C3 also. So 2 plus 3, that's C1 plus C2. So this, let's call this equation 4. Let's call this equation 5. Tama? So with this, they're just the same. I can say that actually from equation number 5, sorry, that's C2. I wrote C3. I can say C1 is just negative C2. Okay. So let what? C2, C1, and then C3. If we let C2 be equal to what, guys? 1. What is C1?
Negative 1 po.
Okay, what about C3? Positive 2. Very good. So that means your third equation, C3, negative 1, 1, 2, e to the t. Therefore, finally, our answer is, what's the first one? C1110, 110 e to the 3t plus C2 negative 1, 1 negative 1 e to the negative 2t plus C3 negative 112 e to the t. And then when you check, some of you might ask, sir, is it linearly independent? Yes. The Wronskian that you'd be able to solve is negative 6.